All right, I wanted to make a video of number 18 on this homework in case we didn't have time to go over it in class. I felt like it might take a little bit of time. It's a relatively long question. So it begins with understanding the difference between an empirical formula and a molecular formula. So if I were to use H2O2 as an example, H2O2 is a molecular formula. It describes a molecule that has two O's and two H's all stuck together. That's not the correct final thing, but it's showing you the molecule. An empirical formula is only showing you a ratio. So if this is the molecular formula, then the empirical formula is just HO. I've divided both by 2. The H's and the O's have a 1-to-1 relationship. Now, it wouldn't ever really make sense to turn a molecular formula into an empirical formula because you want to know what molecule you have. But this question is an example of when you're analyzing an unknown substance, a lot of times the empirical formula is where you'll be able to start. So you figure this out first, and then as you develop more information, you can convert it into the actual molecule you're working with. So let's look at this problem. A compound containing C, H, N, and O is analyzed. So we know what the 4 main elements are. They've probably done other tests, but they don't know the amounts of those elements. They know in fine detail the mass of their sample, and they burned it in excess oxygen to form 2.241 grams of CO2. And when they analyzed it, they found that it contained that many grams of hydrogen. So we know of the 1.23 grams of CHNO, whatever that is, 0.06 grams of it came from hydrogen. Our goal is to be able to figure out the mass of all of the other things. So part I right here says determine the mass in grams of carbon in the sample. Well, I know that I started with 1.23 grams of all 4 things, and I ended with 2.2 grams of carbon dioxide when I reacted it with oxygen. So that means the carbon from my carbon dioxide must have come exclusively from my original substance. So all I have to do for part I is determine if I have 2.241 grams of CO2, how many grams within that are pure carbon. So we need to convert the grams into moles. So 1 mole of CO2, and then we can take the molar mass from our periodic table. I've got oxygen is 16 times 2 plus 12.01 for my carbon. So 44.01 grams of carbon to moles. This is CO2. The reason we're doing that is because we want to be able to convert from moles of CO2 to moles of just carbon. How much carbon is in this substance? Well, because there's only 1 carbon in every molecule of CO2, that's a 1-to-1 ratio. And now that I have moles of carbon, I convert it to grams of carbon. 1 mole of carbon weighs 12.01 grams. When we do the math here, 2.241 divided by 44.01 times 12.01, I get, let's use 4 sig figs, 1, 2, 3, 4, 0.6116 grams of carbon are in my original sample. So now I know if I were able to take the individual elements out of my original molecule, I would have that much of carbon and 0.06 of hydrogen. Let's go on to number 2. When the compound is analyzed for nitrogen content only, the mass percent of nitrogen is found to be 28.84%. Determine the mass in grams in the original 1.2. So this is really easy. If I have 28.84% nitrogen, all I have to do is take the 1.2359 grams of the original substance and multiply it by 0.2884 to figure out the Nitrogen, 1.2359 times 0.2884 gives me, and we're using 4 sig figs again, 0.3564. So I have 0.3564 grams of nitrogen. That was just a percent question. Number 3, determine the mass in grams of oxygen in the original substance. Well, we were given hydrogen, we found carbon and nitrogen. So for part 3, if I were to add C plus H plus N plus O, I should get 1.2359 grams. So I just need to subtract all those other things that I found. 1.2359 minus nitrogen, 0.3564 minus carbon, 0.6116, and then minus hydrogen at the top over there, minus 0.0648, and I get 0.2031 left. So 0.2031 grams of oxygen in my original substance. So now, how do I determine the empirical formula of the compound? If I know the mass of each of my substances, the empirical formula is going to be the ratio of atoms. And so I need to convert each of my masses into something that is a particle count rather than a particle weight. So that means everything needs to go into moles. So carbon, hydrogen, nitrogen, oxygen. How do I convert grams of carbon into moles of carbon? 1 mole is 12.01 grams. So in each case, I'll need to divide by the molar mass. So my carbon was 0.6116 divided by the molar mass to get me moles. 0.6116 divided by 12.01, and let's say 0.05092. 0.05092 moles. Hydrogen, I have 0.0648 divided by molar mass of hydrogen. 0.0648 divided by 1.008 gives me 0.6429. 0.06429 moles. Nitrogen, I have 0.3564 divided by the molar mass of nitrogen. 0.3564 divided by 14.01. 0.02544. 0.02544 moles. And then finally oxygen, I have 0.2031. 0.2031 divided by the molar mass of oxygen divided by 16, and I get 0.01269. 0.01269 moles of oxygen. So that's how many particles I have. We need to figure out the ratio of these particles. The way we figure out a ratio is I'm trying to convert them into whole numbers. But this is experimental data, so it's never going to be perfect whole numbers. So what we do is we need to divide by the smallest one. The smallest number in a ratio should be 1, unless it's greater than that ultimately. And so if I divide each of these by 0.01269, divided by 0.01269, divided by 0.01269, divided by 0.01269, divided by 0.01269, this should get me really close to a whole number because we live in a discrete world that is made up of whole numbers of things. So that one is a 1. 0.02544 divided by 0.01269 gives me 2.00. If I take 0.06429 divided by 0.01269, it gives me 5.07. 5.07. And if I take 0.05092 divided by 0.01269, 4.01, 4.01. So each of these is noticeably quite close to a whole number. What this is telling me is I probably have 4 carbons, 5 hydrogens, 2 nitrogens, and 1 oxygen as a ratio. I don't know if this is my molecule because my molecule could be twice as big of these. Remember when I said hydrogen peroxide, empirical formula was HO, it was 1 to 1, but empirical formula could be describing H2O2 or H3O3 or H15O15. As long as it's 1 to 1 ratio, they will all have the same empirical formula. So we have found the empirical formula. We're done with part A. Now, part B is going to walk through, can you convert an empirical formula into a molecular formula? They're using a completely different molecule, mostly because it would be a pain to grade if they asked you to keep moving forward with this same molecule, because if you've made a mistake anywhere in the process, they have to grade through. So they decided to start from scratch with a new empirical formula. So all I know so far is that I have the same number of bromines as carbons, and I have twice as many hydrogens, but I don't know what the molecule is. It tells us that the vapor density is 6 grams per liter, and it gives us the temperature and the pressure. If I'm seeing all these sorts of things, I find that I'm probably going to be using my PV equals nRT equation. PV equals nRT. The first thing it asks me to find is molar mass. Now, a bunch of the problems on this equation, or on this homework, we're combining a bunch of different equations from your equation sheet. So on your resource equation sheet, I've got PV equals nRT. We also have just an equation for converting mass over molar mass into moles. And we know that density is mass over volume. I want to try to combine all of these things together so that I can have one equation that can take the things that they've given me and convert it into molar mass. So how can I combine N into PV equals nRT? Well, I can say PV equals, instead of N, I can say little m RT over big M. And big M is what I'm looking for, but I haven't been given a mass, I've only been given a density. So I want to try to replace that mass with density information. Mass equals density times volume. So now I'll say PV equals, my little m is going to turn into dV RT over big M. And then molar mass is what I'm trying to solve for. So I'm going to multiply both sides by big M and divide both sides by PV. So I get dV RT over PV, and my V's cancel out. So the ultimate equation I'll be using is density times my gas constant times temperature divided by pressure to get molar mass. And now I should have everything that I need for part I. So molar mass equals, my density is 6 grams per liter. My gas constant is in atmospheres. It's always important to double check that atmospheres is what we're using. So actually, let's write in all of the things. Grams, liter, -1. I'm going to need more space. Come down here. Okay. So that's density. My R value is 0.08206 liter, atmosphere, Kelvin -1, mole -1. Right away, liter -1 and liter cancel out. And then I'm multiplying by temperature, 375 Kelvin. And Kelvin -1 cancels out with Kelvin. And I'm dividing all of it by 0.983 atmospheres. And atmospheres cancel out. What I'm left with is grams and mole to the -1. Gram, mole, -1. Remember, the -1 means it flips to the denominator. So grams per mole is what I'm looking for. All right, all of that work I now do 6 times 0.08206 times 375 divided by 0.983, and I get a molar mass of 187.8. It looks like I have 3 sig figs everywhere, so molar mass is going to be 188 grams per mole. Now, what is the molecular formula? I know the ratio from previous experiments. I calculate the temperature and pressure, and that's able to help me figure out the molar mass. So, if CH2Br was the correct molecule, what would the molar mass be? So, I'm going to add them all together. 12.01 plus 2 times 1.008 for my hydrogen, plus, what's bromine? 79.9. And I get 93.9 equals 93.9 grams per mole. That is much too small, which means I need to figure out the ratio. We can kind of see it's about half, but if I did 188 divided by 93.9, I get a number really, really close to 2. That means my correct molecule is twice as big as this molecule in its molar mass. So I need to multiply everything by 2. C2H4Br2. My original empirical formula told me that my hydrogen is supposed to be twice as much as my carbon. My bromine is supposed to be the same as my carbon. That's correct. But this configuration would give me the correct molar mass. And we can even double check that if you don't believe me. 2 times 12.01 plus 4 times 1.008 plus 2 times 79.9 gives us really, really close to 188. That is our correct molecular formula. So hopefully this helps. Empirical versus molecular is all just math stuff, but it takes some effort to get it figured out.